Okay, so now we're going to look at the difference between what are known as strong acids and weak acids, and we're going to see how this influences our calculations of pH and pOH and other things, all right? So before we do that, we have to remind ourselves of some terms that we learned in General Chemistry 1, namely strong electrolytes and weak electrolytes. And you should recall that a strong electrolyte is one that undergoes 100% dissociation. It undergoes complete dissociation. So, for example, if you add solid sodium chloride to water, then what will happen immediately is that the sodium chloride will dissociate completely to form sodium ions and chloride ions. All right. So if you could see the particles, you will not see any intact sodium chloride units. You would see only sodium ions and chloride ions floating around, surrounded by water molecules. A weak electrolyte, on the other hand, does not undergo complete dissociation. All right. In some textbooks, they'll say it undergoes partial or incomplete dissociation. So a good example of this would be acetic acid. If you add acetic acid to water, then only a small fraction of these molecules will be converted to the acetate ion and the hydrogen ion. So that's the difference between the strong electrolyte and the weak electrolyte. Now we can apply those terms to acids and bases. We have strong acids and strong bases, and we have weak acids and weak bases, right? So let's deal with the strong acids and bases first. A strong acid is basically a strong electrolyte. In other words, a strong acid will undergo complete dissociation. So a good example of this is hydrochloric acid. When you add HCl to water, all of the HCl molecules are converted to the ions, namely the hydronium and the chloride ions indicated there. And we indicate that the dissociation is complete by a one direction arrow shown here, all right? On the other hand, well, not on the other hand, another example of a strong acid is nitric acid, right? Nitric acid, when added to water, undergoes complete dissociation to form hydronium and nitrate ion, all right? Perchloric acid is another good example of a strong acid. In fact, if you have had me for Chem 1, you know that I tell you guys to memorize the 6 strong acids. So let me remind you of them. The 6 strong acids are HCl, aqueous, HBr, aqueous, HClO4, aqueous, HI, aqueous, HI, aqueous, nitric acid, HNO3, and oh, I have perchloric acid. There's one more, which I can't recall right now, but when it comes to me, I'll make sure to include that in this list. All right, but I know there are 6 of them, and these are 5 of them. Um, oh, sulfuric acid, right? Sulfuric acid, H2SO4. That's another strong acid. There's something unique about sulfuric acid. As you can see, it has 2 hydrogens. When it loses the first one, that's a strong dissociation, but when it loses the second one, that's a weak dissociation. I think we'll get to that later on. Anyway, so that's what happens in the case of strong acids. Strong acids are strong electrolytes. They allow for the conductance of electricity because they undergo complete dissociation. Okay. Oh, and here's sulfuric acid here, the last example. The first dissociation, as I said before, is a strong dissociation. So sulfuric acid is also considered to be a strong acid. Now, weak acids are weak electrolytes, such as hydrofluoric acid, right? It undergoes partial dissociation, as you can see here. And as you can see here, the arrows go in both directions. So therefore, that shows you that eventually equilibrium will be established between the products and the reactants. Um, Another example would be nitrous acid, another example of a weak acid. And so the hydrogen sulfate ion is also an example of a weak acid. And even water itself is a weak acid when it reacts with itself to form hydronium and hydroxide. All right, so these are all examples of weak acids. Strong bases, they undergo complete dissociation, such as sodium hydroxide, um, such as potassium hydroxide, and barium hydroxide. They all undergo strong or complete dissociation. Okay, Um, then we have weak bases such as the fluoride ion, all right, such as the nitrite ion, and then we have what are known as conjugate acid-base pairs. So remember, the conjugate acid of a base is what's formed when the base accepts a proton, and the conjugate base of an acid is what's formed when an acid loses a proton. And then what we're going to look at now are relationships between conjugate acids and their respective bases and vice versa. And the first thing that is mentioned here is that the conjugate base of a strong acid is basically weak, very weak, almost neutral. All right. So the stronger the acid, the weaker the conjugate base, right? Another thing you need to be aware of is that the hydronium ion is the strongest acid that can exist in any aqueous solution. So in other words, if you add a strong acid to water, then that strong acid will immediately be converted to the hydronium ion because the hydronium ion is the only acid um, of that strength that can exist in an aqueous solution. If an acid is weaker than the hydronium ion, then the weak acid will basically persist in an aqueous solution. Um, what else? The hydroxide ion is the strongest base that can exist in an aqueous solution. So again, if you add a strong base to the hydroxide ion or to water, then it immediately converts to the hydroxide ion. All right. And what we have here is a list of different acids and their conjugate bases, and you'll see that the acids are arranged in terms of strength from bottom to top, right? And the conjugate bases are on the corresponding conjugate bases are on the right side, and you'll see that correspondingly the base strength increases going from top to bottom, right? So, for example, perchloric acid is a very strong acid. The perchlorate ion here is a very weak base. And then at the other extreme, ammonia is a very weak acid, which makes the amide ion, which is a conjugate base, a very strong base. All right. So basically, there's an inverse relationship between an acid and its conjugate base and a base and its conjugate acid. All right. So just to demonstrate the difference between a strong acid and a weak acid, hydrochloric acid is a strong acid. Before ionization, this is the concentration. And then when added to water, what you'll find is that you have only H plus and Cl minus present. There'll be no intact HCl molecule present in such an aqueous solution. So in this solution, you'll have floating around the hydrogen and chloride ions. In the case of HF, which is a weak acid, what you'll find is that when this is added to water, only a small fraction of the HF would be converted to the ions. So the net result is that you still have a high concentration of HF, but you have also a small amount of H plus and F minus present in the aqueous solution. So that's basically what happens when it comes to strong acids and strong and weak acids dissociating in water. Strong acids undergo complete dissociation, weak acids undergo weak dissociation. All right? Okay, so let's look at this example. What is the pH of a 2.2 times 10 to the minus 3 m nitric acid? So basically, because we know that nitric acid is a strong acid, we know that all the nitric acid will be converted to hydronium and nitrate. And because it's a 1-to-1 ratio between these two, between the nitric acid and the hydronium ion, we know that, let me just, well, this is basically an ice table. Initially, you have 0.002 m of the nitric acid, none of this, and then because nitric acid is strong and undergoes complete dissociation, all of this would have dissociated. So therefore, at equilibrium, you'll have none of this, and you'll have this amount of nitric acid and this amount of nitrate. So since we have the concentration of the nitric acid here, all we have to do is plug it into the pH equation, and we end up with the pH being equal to 2.7. All right. Now, one thing I want to mention here, and I think I should have mentioned it before, and that has to do with how do we round off to the correct number of significant figures when we apply the log function to certain numbers. The rule is that basically, whatever the number of significant figures that you're finding the log of, that should be the number of decimal places expressed in the final answer should be the same. So in other words, because this is expressed to one significant figure, so let me put here, this is one sig fig, that means the answer when you do the log should be expressed to one decimal place. All right? And that is true for any math that deals with log functions, right? Whatever the number of sig figs of the number that you're finding the logs of, then your final answer should be rounded off to the same number of decimal places. All right. Okay, here's another example. Let me erase this so that you can see this properly. Um, okay, what is the pH of a 1.8 times 10 to the minus 2 barium hydroxide solution? Again, the barium hydroxide is strong, so therefore it undergoes 100% dissociation. So basically, you're going to start off with 0.018 m of the barium hydroxide. You would have no barium or hydroxide present initially, and then at equilibrium, this is a state of affairs, right? You're going to have no barium hydroxide. You're going to have 0.018 m barium hydroxide. And here, you're going to have 2 times 0.018 m of hydroxide ions, which is equal to 0.036. And then what we need to do is find the pOH, which is, or the pH actually, which is equal to 14.00 minus a pOH. The pOH would be minus log of 0.036. So when you put a minus log here into this equation, your final answer becomes equal to 12.6. All right, so these are just some simple examples involving the calculation of pH of acidic and basic solutions. All right, okay, let me see what's next here. Okay, in fact, we're going to stop here. The next video we'll look at will deal with some calculations of pH with respect to weak acids and later on weak bases. Okay, until